When most people think of a knot, they think of the standard definition of a knot, which is something like a fastening made by tying a piece of string, rope, or something similar. This seems like a good definition to most, but to mathematicians, knots are something completely different. Mathematical knots differ from the knot you might create when tying your shoelaces due to the fact that the ends of the knots are joined together, creating one continuous strand. But why are they interesting? How are they important? These are some of the questions we hope to answer in this video. Humans have been interested in knots since prehistoric times, mostly due to their aesthetics and spiritual symbolism. However, in the 1860s, Lord Kelvin developed the theory that atoms were made up of knots in the ether, leading scientists, philosophers, and mathematicians to try to tabulate the different discovered knots. Of course, we now know that atoms are not knots, but the question they came up with when attempting to tabulate the knots fascinated mathematicians. What makes one knot differ from another? How do we know that they're not all secretly the same? Before we attempt to answer this question, we should learn some terminology when talking about knots. A knot is an embedding of a circle into three-dimensional space. However, many times we see knots represented in knot diagrams, which are simply projections of a knot onto a plane. This makes showing knots on paper and in videos much easier. Here we have a very simple knot. In fact, this is the simplest knot of them all, as it does not have any crossings, which we will define in a moment. It is considered to be a trivial knot, but it is most commonly referred to as the unknot. An interesting thing to note is that some knots can deform into the unknot. For example, the knot known as the culprit. When one first looks at the culprit, it would seem to be a complicated knot. But through the following transformations, known as Reidemeister moves, it unravels into the unknot. We will define Reidemeister moves and why they do not change the nature of a knot presently. Now, let's move on to a less trivial example. Here we have knot 3-1, which is commonly referred to as the trefoil. The 3 in 3-1 is because this knot has a crossing number of 3. A crossing number for a given knot is defined as the minimum number of crossings that can be exhibited given any knot diagram. In other words, there is no way to draw this knot with fewer than 3 crossings. The 1 in 3-1 is the knot index, which is an arbitrary index assigned to the knot to differentiate it from other knots with 3 crossings. Now that we know some of the notations for knots, we can look at some more examples. Here we have 10 different knots. Some of these knots have special names, like the unknot, the trefoil, and the figure 8 knot. Although some of these knots have the same crossing number, we know that they are not the same. But how do we know this? For example, how do we know that the trefoil is not secretly the figure 8 knot, just twisted up in some way to gain an extra crossing? Or how do we know that they're not all secretly the unknot? We consider 2 knots to be the same if you can deform one into the other without letting it pass through itself. This process of deforming the knot is called ambient isotopy. The culprit being deformed into the unknot was an example of this. In the 1930s, Kurt Reidemeister proved that all deformations can be reduced into 3 moves, which we now call the Reidemeister moves. The 3 moves are the twist, the poke, and the slide. This incredible revelation gives us a way to show if 2 knots are the same. If you can transform a knot into another knot via any series of Reidemeister moves, then the 2 knots are equivalent up to ambient isotopy. This is a really powerful tool, particularly for showing that 2 knots are the same. However, how can it be used to show that 2 knots are different? You might try to deform the trefoil via a series of Reidemeister moves into the unknot. After a while, you might become convinced that they are not equivalent. But how can you prove this? In order to do so, it is extremely helpful to develop what we call an invariant, which are characteristics of a knot that remain unchanged or invariant through Reidemeister moves. One invariant that can be used to differentiate knots is called tricolorability. Tricolorability of a knot is its ability to be colored with 3 colors subject to certain rules. This allows us to create 2 different categories of knots, tricolorable and non-tricolorable. Let's look at how this invariant works. The rules for coloring the knots are as follows. 1. At least 2 colors must be used. 2. At each crossing, the 3 incident strands are either all the same color or are all different colors. Now that we have this tool for differentiating knots, let's try it out. Let's compare the trefoil and the unknot. It's fairly easy to show that the trefoil is tricolorable, as it only has 3 components to begin with. You can simply color each of these components a different color and you have satisfied the rules of colorability. But what about the unknot? Well, since there is only 1 component to the unknot, and we know that Reidemeister moves preserve colorability, there is no way to color the unknot, as it is only possible to use 1 color, violating the first rule of colorability. Hence, we now know that the unknot and the trefoil are indeed different. Let's try a more difficult example. Let's compare the trefoil and the figure 8 knot. Are these 2 knots different? Can you color the figure 8 knot using only 3 colors without violating any of the rules? Try it out. You'll soon find that it is indeed impossible. Therefore, we know that the trefoil and the figure 8 knot are different. We will now show that these rules are indeed an invariant, meaning that applying Reidemeister moves does not affect the knot's ability to be colored. If we try to color Reidemeister move 1, the twist, since we begin with only 1 strand, it can only be colored with 1 color. Applying a twist creates a crossing with 2 components, and at any crossing, rule 2 must be applied. However, there are only 2 components, so 2 out of the 3 incident strands within the crossing are part of the same component. Since each component can only have 1 color, the maximum colors used here must be 2. However, if we had 2 colors here, we could be violating rule 2, hence there must be only 1 color in use. If we try the same technique with Reidemeister move 2, a poke, we see that if the 2 strands are the same color initially, and a poke occurs, the new components must also be the same color. Otherwise, rule 2 of coloring would be violated. If they are different colors initially, we may simply color the additional component the 3rd color, which does not violate any of our rules. Simple enough. How about Reidemeister move 3, the slide? This one I'll leave to you to try, but the idea is the same. In essence, there is no way of manipulating the knot via any of the Reidemeister moves to change the knot's tricolorability. Now that we have seen some examples, a new question arises. Since neither the unknot nor the figure 8 knot are colorable, how can we determine if they're different or not? Let's build on the idea of colorability by introducing another invariant, not determinant. We won't demonstrate why this is an invariant in this video, but for the purposes of the video, we will simply demonstrate how to calculate the determinant of a knot, and how it's related to a more general form of tricolorability. To calculate the determinant of a knot, it is first necessary to number each component and each crossing. Then, create an n by n matrix for your knot, where n is the number of crossings. This allows us to create a matrix with the rows corresponding to the crossings and the columns corresponding to the components. Next, pick a crossing, and in the row for that crossing, place the value 2 in the column corresponding to the component that acts as the overcrossing in the crossing. Place a -1 in the columns corresponding to the undercrossings in the crossing. Place zeros in the column of any component not involved in the crossing. Continue to do this for each of the crossings, and your n by n matrix is filled. Once it is filled, delete a row and column in the matrix and calculate the determinant of the new matrix. The prime factors of this determinant correspond to the number of colors that may be used to color the knot using the coloring rules. Hence, the tricolorability invariant is just a subset of the more general p colorability, where p is prime. This is a much more powerful tool, as it allows us to distinguish many more knots compared to tricolorability. We have merely scratched the surface of an incredibly deep topic, and now we challenge you, the viewer, to continue to dig deeper into knot theory and to explore its glorious properties.